Hi everyone, this is Arya with the second installment in our LTSpice tutorial series. In this part, we will learn how to verify the superposition theorem by using the dissipated function of LTSpice. And we'll also learn how to discover a circuit law, quote, experimentally, unquote, because we will be using a simulator, by stepping a resistor and plotting the values. To begin, we will create a very simple circuit which consists of only a voltage source, a second voltage source, and a single resistor. We'll assign this node as the ground node, and this is our circuit. The superposition theorem says that if this source has a voltage, let's say 5 volts, and this source is turned off, there will be a certain current passing through this resistor. Let's say I subscript A. If this is turned off and this is turned on, let's say 10 volts, you'll have a different current, I subscript B. If both of them are turned on, then you'll have yet another current passing through the resistor called IC. The superposition theorem says that IC equals IA plus IB. The idea of this being, of course, that you can turn on each source individually, calculate the value that passes through the resistor, and then add those values to obtain the final value. This works for linear circuits such as this one and in certain other very specific cases. So let's go ahead and simulate this particular circuit. We will create a new schematic. We'll take a resistor, put it in. We'll go to components, search for the voltage source. There it is. Add one here. And now we want to rotate this one. So we go to this button, or of course we can also use Control R as a hotkey. Now we connect all of them with wires, just like this. Whoops. There we go. The LTSpice simulation can get a bit messy. If you misclick, for instance, in creating a wire, it sometimes creates these very annoying extra hanging bits of wire. In order to correct them, you just press delete. You have to press delete first, and then go ahead and remove the wiring that's incorrect and try again, like this. Now that we have all of them connected, we put in the ground node. This is extremely important. And as an extra step, which is basically optional, but it's really helpful to do it because it avoids confusion later on, we'll just label the node that the resistor is on as, let's say, resistor. This way, it will have a very specific name. And now when we run the simulation, it's going to say voltage on the resistor instead of just saying voltage on node 1. Now with all of this in place, we are ready to assign values to each source. So let's go ahead and do that. As in our circuit, we will assign 5 volts to this one and 10 volts to this one, and we will put an arbitrary resistance value, say 5 kilo ohms. Now with all that in place, we are ready to run the simulation. First of all, we need to specify a simulation directive. In this case, we are going to DC up point. As you can see, there are no options, so just hit OK and put it anywhere in the circuit. Oops. Now you can go ahead and run the simulation. And unlike last time where we had a graph, this time we only have these values right here. We see the voltage across the resistor, and now it's obvious why we named it instead of just labeling it a node, because then we wouldn't have known which one of these is which. So let's go ahead and put the voltage of the resistor and the current through the resistor in a data table to verify the superposition theorem. So this is situation C with both of them turned on. So V through the resistor, I through the resistor, and this is situation A, situation B, and situation C. And in situation C, the voltage through the resistor is 15 volts, and the current is 3 milliamps. We have 15 volts and 3 milliamps. Now let's go ahead and turn one of these sources off. We do that really easily just by assigning it a value of 0. Now we're ready to run the simulation again. This is our A scenario. Has a 5 volts over the resistor and 1 milliamp over the resistor as well. So we have 5 volts here and 1 milliamp. Now we are ready to turn this source back on. As you can see, it is a pretty clunky way of simulating this. The reason I am bringing this up is because in prior versions of this course, this was actually a homework assignment. And I think it would be really helpful to go through this today as well. So we'll run the simulation again. Now we have 10 volts and 2 milliamps. So let's write that down. 10 volts and 2 milliamps. Now it becomes really clear that the superposition theorem holds in this case, because 5 volts plus 10 volts does indeed equal 15 volts, and 1 milliamps plus 2 milliamps does equal 3 milliamps. Of course, this is no proof of the superposition principle in general, but it's easy to see that it does hold in this particular scenario. Now to move on to the second part, we wish to discover a circuit law experimentally. Now, what we're referring to, of course, is, say we have a voltage source that has its own series resistance, and we put in a power consumer, let's say a light bulb or a heater or something like that. So let's assume we have 100 volts over the power source, and let's say that the series resistance is 20 ohms. Now what happens? The idea is that this resistor can take on several values, but there's one specific value of the resistance that maximizes the power that goes through this resistor. So how would we go about simulating that? We go ahead and we create a new schematic in LTSpice. We can close this one. And we add a resistor and a voltage source. We will connect them. And now that we've connected them, we will of course add the ground node, as always. We cannot skip this step. And now that everything is added, we press escape. Then we right click on the voltage source and we assign it the values that we have thought of in the circuit, 100 volts and 20 ohm series resistance. Now this time we want to step the resistor. So we will not assign it a specific value. Instead, we will assign it what's called a parameter that we can change procedurally. A parameter is denoted by surrounding it in curly braces, like this. So now we have a parameter called R that we can change. Hit OK, and now we are ready to roll. Now, if you go to the simulation panel, we don't really see anything that might be of help. However, as you can see, we have this button called Edit Text on the Schematic. We can press either one, select Spice Directive, and now we have a very specific syntax, .step, param. Our parameter is R, and we want to step it from a value of 5 ohms. It has to be more than 0. It has to be a strictly positive value. Up to 40 ohms in increments of 0.2 ohms. So let's do that. Hit OK. Put it anywhere. And now We are not done yet. We need to go to DC out point. We have this .op here. Hit OK. Put that anywhere as well. And now we are ready. We run the simulation, and as before, we click on any specific component, and it will tell us the current as a function of the resistance. It will tell us the voltage as a function of resistance. But we want the power, which is the voltage multiplied by the current. We have two ways of doing this. We hold left Alt and click on it, and this will show the power. Another way, let's remove these. Another way is with this window selected, go to Plot Settings, add Trace, and you can see all these values right here. So we can have V of N001 multiplied by I through R1, hit OK, and it's the same thing. In the graph, we notice that the maximum value of the power is attained when the resistance is 20 ohms. So when R is equal to the series resistance, which is 20 ohms, the power through the resistor is maximized, as we know from theory. This concludes our tutorial. We have used DC out point to verify the superposition theorem, and we have stepped the value of a resistor to discover a circuit law experimentally. My name is Arya, and this concludes part 2 of the LTSpice tutorial for E3081. I hope to see you in class. Bye goodbye.